yeah, I guess this is my take on telling you of what we learned from our journey to port VASP to GPUs. So I've been on this project for more than 5 years now. And I think the best lessons learned from VASP is just if we look at the history of how VASP was ported to GPUs, because there's, yeah, it's longer than those 5 years that I'm on it. Yeah, just to give you an introduction to me, I joined NVIDIA as a dev tech. That is what Phil has already mentioned, are the people who help code developers how to best leverage NVIDIA's hardware. But these days, I transitioned to a management position and still lead a group of dev techs who focus a lot on computational chemistry codes and life science. All right, so yeah, this is what I have on my plate for today. So the introduction to VASP will be pretty short because Phil basically explained everything, and VASP and CUDA, they kind of do the same thing, right? There are subtle differences in some regards, but that shouldn't matter too much for what we are concerned with. And then I have a couple of key lessons learned. So basically, this is unified source across architectures is key for maintainability. Best coding practices or following those are key for good portability, and good acceleration completeness for the features that your code offers is the key for good adoption in the community. And then my final point is that whole application optimization is really the key for good optimization. All right, so yeah, for the introduction, yeah, as I already said, VASP is a material science code. Yet again, also solving the Schrödinger equation. It's targeting mostly solids, but you can also calculate molecules with it if you want to. It also does mostly DFT in the PAW parameterization or basis set. And it can do hybrid DFT as well, which is adding exact exchange, which is basically what Phil mentioned was the NLXC parts. And VASP can even go beyond that. So if you do have some computation that need more accuracy or really care about the unoccupied bands, you can do that in VASP as well. Yeah, so why is VASP important to us at NVIDIA? It's simply because it's one of the most used application in computation centers around the globe. So yeah, I have some examples here on Archer. Yeah, pardon me that it's a bit dated, but that was the topmost used application in, yeah, well, March in 3 years ago. And it's a bit dated, but yeah, I'm quite sure that today it will not look that much different. And that is why we care that it runs well on our hardware, right? And that's why we got involved in the project. So originally, the code is developed by Professor Kress's group at the University of Vienna. There have been various external contributions. I'm not even trying to list them all. And these days, they've spun out a company called VASP Software GmbH. The code has been around for more than 25 years and keeps being developed and refactored since then. It's more than 500,000 lines of code of mixed Fortran. So there's some Fortran 77, there's some Fortran 90, and even newer stuff in it, which doesn't make it a lot easier for us to port. In terms of the frameworks to use parallel architectures, there is MPI. They had OpenMP added for the CPU parallelization. And then even before 2011, there were the first endeavors to leverage GPU acceleration, but then with CUDA-C. I'll get back to why that was in a minute or so. And then most recently was the introduction, well, 3 years ago, but with the introduction of VASP 6, they have added a new OpenACC port for GPU acceleration. And I'll tell you why they switched also later in this presentation. So on the computational characteristics, given that it's doing the same thing as custom scientifically, it's not a big surprise that we have the same computational characteristics. So also VASP is doing lots and lots of small FFTs. So they rarely go beyond 300 to the third in terms of the sizes. And of course, there's a lot of BLAS functions being called as well. It's metrics vectors. we have to diagonalize the matrices. There's also the all-to-all communications that Phil has already mentioned for CUDA. And then, of course, there's also quite a bunch of custom kernels, which makes VASP a sort of flat profiled application. And by that, I mean that there is not this single kernel that takes 80% of your runtime, and basically you optimize that one and you're done, right? So yeah, I would say it's more like FFTs might be around 30%, and the blast operations maybe another, and then everything else is custom kernels. But that really depends on the data set or the benchmark that you're looking at, and it's easy to shift that around. So I'm not, please don't hold me to those numbers. Not a big surprise, because this story for the VASP development team is quite similar. They're also a rather small team. So for them, having a unified source to work on is also very important in terms of the maintainability. And regarding the GPU acceleration in VASP 5, they have done it in CUDA-C, while VASP is Fortran, right? So at some point, you need to hook into the existing code and pass over the work to the CUDA-C kernels, right? And the way it was done was that there is this original Fortran source tree. And I'm just picking a random file here, which is the Davidson solver source code. And that one was duplicated, right? Which one is then called Davidson_GPU. At build time, there is a switch for the build system that allows you to build the GPU version, and then it will just compile the GPU suffixed file instead of the original one. And in that file, you have the hooks to the C interfaces, where then again, there is a file that calls and launches the CUDA kernel. So that already sounds a bit messy, but if you look at it at a higher level, that basically means you are getting two call trees, right? So there's one for the GPU and there's one for the CPU. And of course, they need to do the same thing, right? And that means while you keep developing your CPU code, you have to keep up for the GPU code as well. When you make a change like a fix, or you have an idea on how to improve performance algorithmically, you need to carry that forward to the GPU. And in the worst case, you need to touch 3 files, right? And that is something that you don't want to, because it's just yeah, some extra time on your workload, and you don't have time, right? That's always. And that kind of also led to long development cycles if you want to have newer features on the GPU as well. And there's also what Phil already mentioned, that whenever there is a new hardware architecture from the same vendor, you want to tune your CUDA kernels because there might be new features in the hardware that you want to leverage, and that is just something you need to take care of if you want maximum performance. So that is why there was a change from CUDA-C to OpenACC, because that allows you to do everything from the unified source code. And what Phil said before is that you sacrifice some performance by using OpenACC over CUDA. Yes, in the end, I think that can hold true, given that you don't have all those hardware features necessarily exposed to you as the programmer. But on the other hand, there's also quite a lot of good that OpenACC can do for you, because assuming that you need to write a reduction, there's just so many things that you can do to end up with less than ideal performance if you write it yourself. And OpenACC, if you tell it to do a reduction, it just knows how to do this ideally for each of the architectures that you might compile it for, and you get perfect performance. Right, so in that sense, especially when you're new to CUDA, I wouldn't be surprised if OpenACC actually can give you some better performance than when you do it on your own. So that is also just something to keep. So one of the key challenges to port VASP with OpenACC was handling the data structures, because VASP is full of aggregated data structures with derived types, and they're deeply nested into each other. We just have schematic here on the right to show you just one example of that. And that kind of makes it not an option to use OpenACC with unified memory. And for those of you who don't know unified memory, that's the possibility for you to only focus on writing the kernels, and the CUDA runtime will detect when you need the memory on the GPU and copy it over transparently, just like a page fault. Right? That's one way to look at it. But since some of those data structures have static members, which cannot be detected by the runtime, because they can reside on the stack, right? Then you can't just detect a page fault. So that didn't work. These days, with H&M support in the kernel, you could try it again, but that is now and not back then. So what we did was something we call manual deep copy, which basically takes care of transferring over these data structure trees to the GPU and back again. Just to give you an outline of what you need to do in OpenACC or how that might look like. This is one of these, well, it's an example on how such an aggregate data structure might look like. And what is important is that you do the copying of the parent structure and then of the member in exactly that order. Because there's just some complexity the OpenACC runtime needs to take care of for you. I'm not diving into the details for that. But that was just one of the learnings that we found very important for complex code as fast. And then, as well said, leveraging libraries that can do mass functionality for you. That is also just important to get A, good performance, and B, progress quickly on your porting efforts. So in VASP 6, we use QBLAST for BLAST, QFFT for the Fourier transforms, QSolver for all the metrics diagonalizations. And we do use Nickel, which is a GPU-centric communication library, to do those communications from the device where they originate, right? So CUDA-aware MPI can do the same, but it's not streaming aware. So you will still have the data transferred from one GPU directly to another, but you might need to take care of the synchronization. And because MPI doesn't know about GPUs from the outset, so that is just one extra synchronization which might slow you down. And for the libraries, this is just a slide to show you how you can nicely encapsulate the source code so that it still looks like a native, say, a CGEM call, right? There's this prefix, you are free to call it whatever you want to, but basically the rest is the same. And then there's just a small code load, if you want to call it that, that takes care whether you want to load it off to the GPU using OpenACC or just use the regular general CPU. Okay, so I have this section telling you to follow best coding practices, and I have only one slide on this, but this was really something where we struggled with VASP in the beginning. So basically what I'm telling you is do initialize your variables, because I know there have been quite some compilers around that used to do this for you in the past, but I think even those have moved away from that practice, and that will just give you a lot of headaches when you need to debug this. Same holds for pointers, which basically in Fortran you don't need to initialize them if you know what you're doing, but that is programmer knowledge. And the OpenACC runtime sometimes needs to rely on a pointer being initialized or nullified once you're not using it anymore. So basically, it's good practice not to leave them dangling and say, well, point to now when you're not pointing to something. That will make your life a lot easier, but that's independent of GPU acceleration. And also something we found, especially when you're mixing different levels of Fortran standard, that there can be situations where a temporary array is created transparently from the programmer's view when you pass an array between subroutines. That happens when a compiler can't know at compile time that the array say, for example, is contiguous in both cases, because it might have not been before, but after it is, then you create a copy, right, that is contiguous. And then when you jump back to the calling function, yeah, you just restore or copy the data back to the originating array. And with OpenACC, that can, because basically that is a different array that can confuse the runtime. So yeah. And basically what I'm saying is when you have code that works on many compilers, then you are portable, and then it's much easier to yeah, target accelerators as such. Right. So yeah, my next section is about feature completeness in terms of acceleration. And my first slide will just show you a decision tree on what features to use in VASP. So basically, I would say VASP is a Swiss Army knife for quantum chemistry, even though it's made in Austria, but yeah, excuse my subtleties here. So I think on the first level, you can choose what level of theory you want to go with, right? There's standard DFT, hybrid DFT, there's RPA, BSE, and probably a lot more that I'm not even trying to put on this slide. And then going along with basically each of these methods is a set of solvers or algorithms that can be used to yeah, get the result. So Davidson is a stable solver, RMMDIS is a faster solver, you can combine those to get a stable but fast result. And there's also the direct optimizers that go along with algo damped or algo all for those fast users among you. And then yet again, unrelated, you can choose the projection scheme. I'm not diving into the details, but basically sometimes you stick with the reciprocal scheme because it's more accurate. But the real space scheme is yeah, a lot more efficient, especially when you are targeting big systems. And then there is three kinds of executable flavors in VASP. So the gamma point executable flavor allows you to do a mathematical trick when you only work at the K point that is centered at the at 0, 0, 0, which is called the gamma point. And then there's a bunch of parallelization options. And basically, the selection of what you choose here, that will determine how well, or if at all, your calculation will be GPU accelerated, right? So we have heard a lot of people say that for VASP 5, when we asked the question, are you using it on the GPU? They said, oh, no, I really can't, right? And we said, oh, why not? And they said, well, yeah, that is because I need feature X, and feature X is not accelerated on the GPU. And that is, of course, something where we do understand that people would say, okay, I'll just stick to the CPU if I can't rely that all the features that I need will be accelerated. So we tried to figure out what the most important methods are. So please note that these diagrams are based on job count and not on computation hours. So because it says basically everything is standard DFT, right? And only 5% or something is hybrid DFT. But if you keep in mind that hybrid DFT is much more expensive than standard DFT, it might offset that and come up with a much bigger percentage on the computation hours. Same holds for RPA and BSE. They are just much more expensive again, even than hybrid DFT. So seeing them pop up in this chart means they are not entirely eligible. And same holds for the solvers. So Davidson, which is the default, is the most important. And then there's RMMDIS in this blue and green parts. So that is what we sought. Having hybrid DFT and standard DFT with those three solvers, that is the bare minimum that we need. And what is not shown on the slide, the gamma versus standard executable flavor, they are kind of 50-50. And we kind of need to get those working. And if you look at this slide, which tells you what was accelerated in VASP 5, well, it looks like it's good enough if you don't care for gamma point application, simplification and the reciprocal space. But then there are subtleties like most people who did hybrid DFT combined that with the direct optimizers, and that was not accelerated, or at least not well accelerated. You can run hybrid DFT through Davidson, but then you pay a 3x penalty because that is what it's more expensive in that algorithm. So yeah, we saw that this is quite a limitation on VASP 5's CUDA port. And with VASP 6 and the OpenACC port, sorry, basically everything that is in bold green here is an added functionality in VASP 6.1 for OpenACC support. And we've rewritten everything that was GPU accelerated in CUDA before, but is now also in OpenACC. So that kind of gives you a feeling on how much faster you can progress with OpenACC to tackle all the features. So basically, right now there's none of these limitations anymore. Because if you want to do hybrid DFT, you run it through the direct optimizers. That's accelerated. If you want to use gamma point, not an issue anymore. If you need reciprocal space representation for phonon calculations or such, you can do it, right? So yeah, and with VASP 6.2, there is linear response. We have support for MetaGGA and Van der Waals DFT. So in January, VASP 6.3 was released, and that release focused most on optimization and development on RPA, but that did not make it into 6.3. But yeah, I think it will be in the next release. So yeah, but basically, if you want the customers of your application to really go for GPU acceleration, then you have to offer them a good enough set of features that are accelerated. And then my final point is that you really need to think about whole application optimization, because as I said before, if you have that 80% kernel, you think you could get away with optimizing this, which might be true. But keep in mind, there's Handel's law, and if you only accelerate 50% of the application, the best speed up you can theoretically get is 2x, right? So yeah, we need to run and profile the whole application. So for VASP, that first meant for us that we need to take a look at all the different parallelization layers, because there are implications for this. So that's simply those 4 or 5 layers. I think it's 4 because the wave function is just the topmost structure. So there's spins. VASP does not parallelize over spins. There is k-points, if that makes sense to you. There is an option to parallelize over them because they are more or less embarrassingly parallel. Then there's the bands or the orbitals, which is the default level for VASP to parallelize over. And you could also parallelize over the plane wave coefficients, as Phil has already said. And that is the part where you introduce those communications within the FFTs and render the 3D FFTs into 3 sets of one-dimensional FFTs. And so k-point parallelism, which goes under the k-par option in VASP, that is an obvious thing to want, but there's calculations that can profit because they only have one k-point. So if you have it, you want to go for it, it helps you with scaling, right? Nzim is a VASP-specific parameter that simply influences how the orbitals are blocked, because you can do, say, one orbital, then apply all the operations to that orbital, and then proceed to the next. On the other hand, you could say, okay, let's take 4 orbitals, apply each and every operation to all 4, then proceed to the next operation, and so on and so forth. And that influences caching behaviors. So that is important, especially for, it's worth to point out that the ideal value differs between the CPU and the GPU. So if you are not seeing the ideal performance, I strongly recommend to look into setting this parameter. And then there is this ncore flag, which controls whether or not and how many GPUs would take part in the FFTs. And we found that whenever you split this, this is detrimental for performance. So we did an implementation for this and it worked, but given that it always was bad for performance, we are just overriding it in VASP and set it to 1. So we always go with the band level parallelism only, just so that users don't run into bad performance, because they are used to setting it to a high value, because that is what you do on CPUs. Okay, this is a short comparison between what we had in CUDA and what we have now in OpenACC. So this is a subsection of the orthonormalization routine. And in that, we need to redistribute the wave function. That is an all-to-all call, right? And in the CUDA part, we did it with host-only MPI, but there's CUDA-aware MPI, and that just has some shortcuts. So you definitely want to use this. Then there is a bunch of matrix multiplications, but when your data resides on the host, which is the only option if you use host-only MPI, you need to stream the data in, similar to what Phil explained with the FFTs, to keep the GPU busy. But when you leave the data on the GPU, well, it's faster, right? Because you don't even need to stream it, and you can just fire off the kernels. The code speed decomposition has been done on the CPU before. Well, if the data is on the GPU, use it, right? It's twice as fast. So basically, I think the outcome of these first sections is when you can leave the data on the GPU, do it, right? Don't pay the extra round trip for going back to the CPU. Then when you're doing matrix multiplication, there was a scheme where VASP said, okay, well, we know that we don't need to update each and every block of the matrix. We just go with those that we need to update. And this blocking scheme has a parameter on determining the block size, and going with bigger block sizes is better for GPUs. So that's also where we could save quite a lot. And then there's this GPU-aware API again. So yeah, getting close to the end of my presentation, I just want to also show you some performance comparisons. So this is just the details on the benchmark. I'm not calling those out. I can send you the slides, or you can watch the recording if you care for those. And also, please keep in mind that these are not the latest and greatest performance numbers, but I really wanted to compare to what we had in VASP 5 and to what we have with the CUDA, with the OpenACC part. So basically, when you measure new numbers, expect it to be a lot faster than what we see on this slide here. So yeah, basically, I think the message is with OpenACC, we get 2x the performance that we had on VASP 5 with CUDA-C. And that comes down to we were able to really port much more and more code in OpenACC that has ever been done in CUDA-C, simply because of the overheads that came along. And basically, it comes down to looking at the whole profile, the whole timeline, and getting, I'd say, something like 90% or 95% even, depending on the benchmark, running on the GPU. So yeah, I guess this final benchmark stands a bit out of the others, so I'm saying a bit about it. So this is a hybrid DFT calculation, and I think what is most notably is in VASP 5, you couldn't run it like this on the GPU because it was using the gamma simplification. Well, you could do it, but you would pay a 2x penalty. But yeah, then technically you're running a different calculation. And yeah, I think we've just had some amazing results in terms of the speedups here. So yeah, so let me sum up our key lessons learned for whole application performance. When you do some porting, please port and optimize in cycles, because whenever you have ported something, your profile changes, and what seemed not to be important before can be a bottleneck after your first ports. And keep profiling, and always, I know this is hard because when you're very familiar with the code, you think you know the code. However, keep profiling it, do it anyway, because there might be surprises that happened to me as well. So I've called out Amdahl's law before. One more important point is to use asynchrony whenever it's possible, because the GPU can run asynchronously to the CPU, and you want to exploit that. And what Phil also said definitely applies to VASP as well. When you can batch multiple instances of a kernel, do that, because it especially helps with small data sets, because it GPUs are massive parallel processors, and you need to keep them filled for good performance. And also refactoring kernels or even higher level algorithms to keep the GPU fat or to just express more parallelism at the same time. That is really helpful. So I think we're right at the top of the hour. I hope we still have time for a question or two. But that's what I have. Thank you.
Thank you, Stefan. I see a comment / question from Ye on the chat. I'm not sure it's related to your talk specifically. So while he typed the full question in case it was related, I have a quick question for you. So you mentioned about the use of nickel directly in the code, and we talked about nickel this morning. Our colleague Gili mentioned about it. So my question is, so does the use of nickel and the use of NVLink matters a lot for VASP? If there's no NVLink, I mean, what kind of penalty eventually you will see?
Yeah, so even when there's no NVLink, nickel will still help you, right? Because nickel can communicate from one GPU using the PCIe bridge to another GPU. It can even communicate over the InfiniBand network, right? So nickel is not a prerequisite. And what nickel really helps you with is it's streaming aware. So you can just put, say an all reduce into a stream as you would a kernel, right? And the interface is similar to MPI, just with the major benefit that, well, it works just as asynchronous as a CUDA kernel, while for MPI, you either need to do a full synchronization with the GPU to make sure nobody's operating still on the data that you want to communicate. Well, you can also communicate asynchronously with MPI, but that's, a lot of effort in terms to implement. So yeah, I'm highly recommending having a look at it if you do have communications.
And yes, go.
I was thinking I just asked question directly. So in the ACC gem call you showed, it seems that there's an if statement, and seems that you could actually at runtime select using acceleration or not. So is this kind of mechanism exposed to user, allowing user to compile the code once and then turn on off OpenACC part, turn on off acceleration per feature?
Yes, you can do this. So, but you have to do something for your users as a program, right? So OpenACC has an if clause, and that allows you to put in expressions that determine whether or not to execute this kernel on the GPU, right? If it evaluates to false, it will run on the CPU.
Yes, but is it exposed to the users?
From
user input control. No, I'm saying you have that enabled supported by OpenACC, but do you connect it to the user input, allow to user change some input parameter to dynamically turn on off features at runtime?
Yeah, so in VASP, we don't expose this as an in-car parameter or something, but what you can do is if you hide the GPUs, like setting CUDA visible devices to an empty string, right? Then it won't detect GPUs, and then it will automatically revert back to the
I see.
CPU.
So it's still all on or off. Yeah, but in reality, in simulations, for example, we use some additional features, then you realize those additional features exhaust your GPU memory. So sometimes you want maybe the standard FT, the majority portion running on the GPU, get some acceleration, but some additional features, they have OpenACC support, but you want to turn it off. There are scenarios like this.
Okay, that is definitely something one can do, and VASP kind of has the infrastructure, so that would be a feature request that might be good to bring up with the ISV. I can discuss it with them, but I guess it's always better when a user says, okay, I have this specific need, because that might make it easier. But technically, that is possible. Yes.
Yeah. Thank you. I have a separate question in the chat, but that's just clarifying question. You can ask or you can answer anytime.
Yeah, I'm deferring this to Filippo. Do we still have time for this?
Yeah, go ahead for the question. We have time.
Yeah, that is the page migration question.
Yes. I think that... So you have HMM, but you didn't explain what it is. So
Ah, right. Okay.
Maybe
So
to help others.
Yeah, that makes sense. Sorry. So basically, HMM is a patch to the Linux kernel that allows it to detect page faults on the stack as well. And if it, because basically you need access to to the stack level, and that can only go through the kernel. And if you have this, and I think the newest Linux distributions do, then you can use the managed memory also for the static members that prevented it before, or when we started the port for VASP. So yeah, I would say if you don't have strong feelings about backwards compatibility, then you should try it for your. Does that answer your question?
Yes.
Okay, perfect.
There is a question for Phil. Phil? You're on
Yeah,
mute.
thanks. Lovely talk, Stefan, and I pretty much echo everything that you said. I put in the chat for anyone, there are a couple of times we use different words for the same thing. Quick comment, I would strongly recommend offloading the reciprocal space projectors. We got a really nice speed up from that. I think you'd add nicely to your speed up curves there. And as you hinted at, it's necessary for accurate forces and stresses. So there's a big science case for that. For the CUDA Fortran, the thing that's put us off from the scientific development time is just the maintaining that when you move architectures. Is it, have the VASP team bought into that, or is you as a dev tech, are you supporting that? How does that work, going forward?
Sorry, can you repeat the first part of that?
Well, it's about,
yeah,
sorry. How is that going to be maintained, the CUDA kernels, the bespoke CUDA kernels? Are you going to take that long term, or is someone in the VASP team going to, how's it going to work?
Yeah, so there's an easy answer. It's gone. So I had that on the slide. So in VASP 6.3, they have completely removed the old CUDA kernels. So going forward, VASP is only OpenACC.
I missed that bit. Okay.
Yeah, I didn't call it out, but it's a subtlety. But they have, I think in 6.2, they have deprecated it because it was just more feature complete. It was faster across the board. So they saw no reason to keep maintaining it. Now it's gone.
All right, thank you. And just, sorry, one really quick one. When you're doing your CPU GPU comparison, the last couple of slides, how many CPU cores was that?
I think that was run on a DGX1 that has a dual socket Broadwell. So I would say that is 40 physical cores. And what I also want to call out, when we compare CPU to GPU, we do full parameter optimization schmooze for either which, right? So we are comparing fastest time to solution on either architecture.
Okay, thank you.